So our unit on fluid mechanics now moves into a discussion of fluids in motion. Last time we looked at fluids at rest, and now we're going to turn our attention to the particles that now are in motion. Okay, and it's very difficult because fluids are made of many particles. They're systems of particles. It's very difficult to try and describe fluids if we look at the individual particles. So instead of doing that, what we're going to do is we're going to look at the motion of fluid, of the entire fluid in space and time. Okay, so to begin our discussion, we need to talk about flow. And in general, there are two types of fluid flow. Steady flow, which is also called laminar flow. And that's where each particle of the fluid flows in a smooth path. Particles never cross each other, and the velocity is constant. Okay, so that's steady flow. Turbulent flow is, of course, as you can expect, irregular flow, where a small whirlpool regions form. All of this happens above a certain critical velocity. And what you can expect is that fluid flow in reality is going to be somewhere in between these two extremes, somewhere in between perfect steady flow and turbulent flow. Because in nature, the flow of moving liquids and moving gases is very complex, it's very difficult to describe in its entirety. So what we say is that we're going to approach the topic, but we're going to make a few simplifications. And so we're going to say that every single fluid that we discuss in here is called an ideal fluid because it obeys the following four assumptions. The first assumption is that the fluid is non-viscous. Okay, so viscosity refers to the amount of internal friction in a fluid, and it generally it relates to how easily a fluid flows. So if you think about something like maple syrup and something like water, maple syrup is much more viscous because it has more internal friction. Molasses is very viscous, and so what we're going to assume is that the viscosity of ideal fluids are zero, so they flow perfectly. The second assumption we're going to make is that the flow is always steady flow. We're never talking about turbulent flow, we're always talking about steady flow, so the velocity of the fluid is going to remain a constant. The third assumption is that the fluid is incompressible, and of course we know that this is not true for gases, and it's less true for liquids. But we're going to say that the density of the fluid is a constant. Okay, it makes things much simpler, and we're just going to make this assumption. And lastly, the flow is irrotational, which really means it doesn't twist or spin. Basically, the angular momentum of the particles inside the fluid are zero. Okay, so really when they flow, they're flowing in one direction. There's no spinning. There's no angular momentum. There's no angular motion. So having said this, we can now say, okay, well, what's a streamline? Okay, and what we say is that when a fluid is in steady flow, the path that each particle takes is called a streamline. So here's a little diagram of streamlines. Okay, the velocity of any particle within the fluid is always tangent to the streamline, and so we've shown that in the diagram. Streamlines do not cross each other, and a set of streamlines forms a tube of flow. And of course, if you've ever watched car commercials where they attempt to show how aerodynamic a car is, they'll show it perhaps in a wind tunnel with little small wisps of smoke that demonstrate the streamlines around the car to show you how beautifully the car cuts through the air and the air creates these streamlines around it. Well, streamlines are basically how we indicate the direction of fluid flow, and they're important to know. So now we come to the equation of continuity, and this is a pretty big deal. It's a pretty big issue in fluids, and we're going to derive what the equation of continuity is. We have this non-uniform pipe, as you can see here, and by non-uniform pipe, I just mean that one end has a cross-sectional area of A1, and the other end has a cross-sectional area of A2, and they're not the same, okay? And so the end with A1, there's going to be fluid that's flowing through that pipe, and it's going to be going at some speed v1. And at the other end, we've got fluid, the same fluid that's flowing through the pipe. It's going at velocity v2. Okay? Now, this diagram is not to scale, but what we should say is that the cross-sectional area times the length, which is indicated by delta x1 and delta x2, those volumes are the same. Okay? And so we've got the same fluid that's flowing, and it's got a density of rho. And let's try and derive this equation of continuity, and you'll see what it means in a moment. In some time t, the fluid at point 1, and we're going to say that point 1 is on the left, where we've got subscript 1, the fluid is going to move some distance, delta x1. And the distance that it moves is v1 times time. And so what we can do is that we can continue and we can say, all right, the mass of the fluid that's moving through that area is given by this mass m1, which is simply the density of the fluid times the volume of this little section of mass. Okay, because mass is equal to density times volume. And so what we can write is, hey, instead of writing x1, let's write that in terms of v1t. We could now do the same for the other side. And we can say, okay, well, over here, hey, what's the mass of liquid through point 2, which is over on this side, the right-hand side of the tube. And we can say, okay, well, mass 2 then is equal to the density times the volume. And we can express this volume in terms of the cross-sectional area times the velocity times time. But we know that pipe moving through a tube is conserved. Mass is conserved. And so from here, we can say that, hey, if some mass goes through point 1 in the pipe in a time t, then the same amount of mass goes through point 2 in the pipe in a time t. And we can say then that rho a1 v1t is equal to rho a2 v2t, and we can now cancel our densities and our times, and we get the equation of continuity, which says that a1 v1 equals a2 v2, which equals a constant. And that's called the equation of continuity. And basically what this says, and it makes sense if you've ever thought about this, is that the product of the area and the fluid speed at all points along a pipe is constant for an incompressible fluid. And you know this, right? If you've got water that's flowing out of a garden hose, and it's flowing out of the tap, which has a certain cross-sectional area, and it's flowing with a certain velocity. If you change the cross-sectional area of the other end, i.e., you put a nozzle on it, what happens to the velocity? If the cross-sectional area goes down, the velocity goes way up. And so we can get our fluid to shoot out at a faster speed. So here's an example of that. A water hose 2 centimeters in diameter is used to fill a 20-liter bucket. If it takes 1 minute to fill the bucket, what's the speed at which water flows through the hose? So let's find V1. And then in the second part of this question, we're going to put a nozzle on it, and then we're going to find the speed of that water. So this is exactly it. It's a garden hose question. So here's what we know. We know the first diameter, we know the second diameter, we know the volume of the tube, of the bucket, and we know how long it takes to fill the bucket. So let's say this. Okay, what flow fills the bucket? So let's figure out the amount of flow that's coming from this tube. And basically what we can say is, okay, flow is just volume in a certain amount of time. So the volume is 20 liters, and of course we can turn 20 liters into SI units by just multiplying by 1,000, because that is then in centimeters cubed. So I get 20 liters, 2.0 times 10 to the 5 centimeters cubed, and it takes 60 seconds to fill the bucket. So the flow then out of this tube is 3.33 times 10 to the 3 centimeters cubed per second. Okay? Well, the equation of continuity tells us that, hey, if that's the flow, if that's what's coming through the tube at any given time, if it's centimeters, if there's 3.33 times 10 to the 3 centimeters cubed, that are going through any point in that pipe in a certain amount of time, I can calculate, I can say that, hey, A1 V1 is equal to that rate of flow, that rate of volume change. And that's exactly what the equation of continuity tells us. So here, if I multiply, or if I divide out by the cross-sectional area of the end of the garden hose, I get a velocity of 1.06 meters per second, and that's the speed that the water has coming out of the hose. In part B, though, hey, we put a nozzle on it, and we say A1 V1 equals A2 V2, and we just rearrange and try and solve for V2. So when we sub in the formula for the cross-sectional area, of course, we're assuming that these are all circles, right? The end of a hose, the cross-sectional area of the end of a hose is a circle, and the same with the nozzle. And so when we do this and we make our little substitutions and we sub in our numbers, we end up with, as expected, a much higher velocity when we decrease the cross-sectional area. So Bernoulli's equation is the last part of this lesson, and it really links the equation of continuity to this whole idea of kinetic energy and gravitational energy. Because Bernoulli was this Swiss physicist, and he was the first one that really looked at fluid pressure, the speed, and its elevation. And so what he did was he said, okay, well, let's look at the work done by the fluid in the first part of the tube, in section 1. Well, we know that work is equal to the force of the fluid times the distance over which that force is applied. And what we get is, of course, force is equal to, fluid force is equal to pressure times cross-sectional area. And we know that area times this certain distance x is equal to volume. So A1 times x1 is equal to volume. And now this diagram is a little bit more to scale because you can see that, hey, the volume of this lower cylinder of fluid is going to be the same as the volume of this upper cylinder of fluid. So let's calculate the work done by the fluid at point 2. And it follows very, very similar. Now here, though, we have to include a negative sign, because we know that as the fluid goes from the lower part to the higher part, we've changed its velocity. Its velocity's gone down. And so the fluid force is in the opposite direction to the way that work's being done. So we have to include a negative sign. And we really do the exact same derivation. We say, okay, work is equal to negative P2 times volume. And we can say, okay, well, then what's the net work? Let's put these two things together. Work 1 plus work 2. And we get P1 minus P2 all times volume. And that's the net work that's done. Now, one other thing that we're going to do before we go on is we're going to say, okay, well, hey, now the height of these pipes are important. So we're going to add in a Y1, some reference on the one side, and a Y2, some reference on the other side. We're going to say, okay, well, the height of the pipe is going to become important in a moment. So we have an expression now for the net work that's done by the forces that are in the fluid. Part of that work goes into the kinetic energy of the fluid. Part goes into changing the height of the fluid. And so here's our expression for the change in kinetic energy. Here's an expression for the change in potential energy. And we know that work is equal to the change in energy. And so we can basically now say, hey, we had an expression for work, we have an expression for kinetic energy, and an expression for gravitational energy. Let's divide the whole thing by volume. So we're dividing the whole entire expression by volume, and what do we get? Well, on the one side, we're just going to get P1 minus P2. But as we will see, mass divided by volume gives us density. And so really, we have the conservation of energy for a fluid. And we're getting very close to Bernoulli's law. Let's rearrange this expression so that we get all the 1's on one side, and we get all the 2's on the other side. And we get P1 plus 1/2 rho V1 squared plus rho GY1 is equal to P2 plus 1/2 rho V2 squared plus rho GY2. And if we take 1/2 of this and call it a constant, we come up with Bernoulli's equation. So let's use this. Let's use this in a couple of examples. The horizontal pipe shown below, and here it is right here, is known as a Venturi tube. It can be used to measure the flow and speed of any of an incompressible fluid. Determine an expression for the speed of the fluid at point 2 if the pressures in the areas are known. So this is really just getting comfortable rearranging Bernoulli's formula, but because what we can say is that, well, really, we don't have any change in height, so we can get rid of the gravitational potential energy term. We got some pressure at point 1, we got a pressure at point 2, and the fluid's moving with a different speed at point 1 than it is at point 2. We can say, okay, we want to rearrange this, and let's find an expression for V. So let's have some fun with some rearranging. So we'll pull the pressures over to one side, and we'll pull the velocities over to the other side. Let's get rid of the half. Let's get rid of the density by moving things around. And now we got V2 squared minus V1 squared. At this point, V1, who cares about it? Because we know that we can write V1 in terms of V2 if we know the cross-sectional areas. And we do know the cross-sectional areas. It's a 2. So let's sub this value of V1 in here, and we'll do some algebra. So there it is. We got V2, we've replaced it. We've pulled V2 squared out as a common factor. We can rearrange, and we end up getting this great term here for V2. V2 squared, take the square root of the whole darn thing, and pull out the A1 in front. And there's an expression for the fluid flow at point 2 in the pipe, the velocity of it, in terms of all these other things. Really, that example is just an expression in rearranging and getting comfortable with Bernoulli's equation. Let's take a look at something more practical. A large storage tank, which is open at the top, it's open to the air at the top, and it's filled with water. It develops a tiny little hole in its side at a point 16 meters below the water level. So this is a massive tank with a tiny little hole. If the rate of flow from the leak is 2.50 times 10 to the minus 3 meters cubed a minute, so not very much water is coming out, determine the speed at which water leaves the hole and the diameter of the hole. This is a quintessential Bernoulli problem where we've got this big tank and it's got a tiny little hole. Okay? And so what we know is that, hey, we know that the top of the tank's open to the air, and we know that the hole's open to the air. So P1 equals P2, which equals atmospheric pressure. We also know that we can set Y1 to be 0. So let's say the top of the vat, the top of the tank, is set at 0. That means the hole is located at some distance Y2, which is minus 16 meters below. Here is Bernoulli's equation. And we can make some simplifications almost right away. We can see that pressure 1 and pressure 2 vanish because they're the same thing. And we can see that Y1 goes away. We also can get rid of our density term. We don't need the density. And so we can rearrange and we can just write V1 is equal to V2. V1 squared, excuse me, is equal to V2 squared plus 2GY2. Now, at this point, we need to make an assumption because we have too many unknowns. But think about the size of this hole and the size of the tank. The tank is massive in comparison to the size of the hole. So we're going to assume that the rate at which the water falls from the top of the tank is way smaller than the velocity that it shoots out of the little hole. Right? So think about a dam that sprung a little tiny leak. We know that that leak is going to shoot water out at a really, really fast rate. But the amount of water, the amount that the water goes down at the top of the tank is not going to be that much. And that's, of course, because of the equation of continuity, which states that, okay, well, the area of the top of the tank is so much bigger than the area of the hole. So because of this assumption, we're going to say, hey, V1's pretty much 0. it's pretty much not dropping at all. It is, but it's imperceptible in comparison to V2. Safe assumption to make. And now we can substitute in our value for y, and we can solve, and we find that V2 is equal to 17.7 meters per second. We can take this information now and we can say, hey, now I can use this rate of flow. A2 V2 is equal to this constant, which is 2.5 times 10 to the negative 3 meters cubed per minute. Turn that into meters cubed per second, and we've got this value. I know what V2 is, and I can find the cross-sectional area of the hole. And now, if I want to find the radius of the hole, that's no problem. Pi r squared, and I can find that radius. Actually, that should be diameter. The diameter is equal to 1.7 millimeters. So through this step, you'd actually find the radius first, and then you'd, of course, have to multiply by 2 if the question wanted the diameter. And that's all she wrote.